Kind of trying to do parallel streams from the same YouTube account and see if it actually works.
Fair enough.
Right. I can see you move.
Indeed, yes.
Fantastic. I've got a little bit of audio feedback.
From yourself?
Can you speak?
I was going to say, I don't think I can hear anything of myself.
Good. Good, excellent. Okay. I'm going to, this is good. What we're going to do is we're going to, right, okay, so the next update is this is a bit of a lone whiz through the paper because the guys have been a bit whacked out after our trip to London yesterday. So I've said they don't actually have to watch it live. So what I want you to do, if possible, is just kind of go through the paper and just like do any interesting things that come up from it. And it's partly as a test to see if it works. Partly it might be just, it may not work that well because, of course, you basically
it'll be an interesting experience for me. I'll be basically live streaming as on my own. It's a good experience.
Basically be a loner. You'll be a Billy No Mates. Yeah. You'll be live streaming, and no one will be watching either live, but no one will be in the room either. And it's kind of an experiment to see if it's possible because it might be a bit too weird. But
I mean, people do this sort of thing all the time. I suspect it'll take some getting used to, but I'm very happy to. I suspect it won't go perfectly well right now, but I'm sure I could practice and make it work quite well actually in future. So yeah,
let's try it, and see what happens. I mean,
it's also a convenient format because it means in the longer term that if we wanted to, I could live stream myself walking through a paper at sort of almost any time. It means that my timeline doesn't have to fit your timeline, or indeed for anyone else doing the same thing.
That is quite convenient. And the other good thing about that is if you were part of a team as we expand, and we had some people who are able to be in Cambridge and physically come into the building, great. But other people might be very good, but they might it just might not be convenient for them to be able to come in. So if it works well, that would be quite useful. Okay, well, just see how you get on. It will be a little experiment, and I still pay you whether anyone's watching live or not, so it doesn't matter.
Right? So final question, because we're starting at 5:30. So do you want me going on till 6:30 or until 7?
I'll pay you from 5 because you're ready from 5, but just go until however long it takes for you to do the paper. Which, if you can do it in an hour, great. If you take a bit longer, it doesn't matter.
We'll take it as it goes then. Yeah. Sounds good.
I mean, within reason, don't spend 4 hours doing it and say, "Oh, Tom,
yes, no." Well, I'm still not going to actually do the calculations on the spot and such.
Of course,
it'll be like a regular lesson, just less interactive. So, I think does that seem like a generally good plan?
Let's try it. See how it goes.
Or, I mean, maybe in future we can aim to actually do the calculations, but that would be considerably longer. So
the thing with the calculations is that they've got the mark scheme as well, right?
Yes, well, exactly. So that was why I was saying I wasn't going to
just show them what too much. Rather than, I mean, what I would do is probably do the bits, take them to the stage where they're actually going to be just plugging the numbers in and doing that sort of thing.
Yeah,
and then just
exactly.
Just in case bring up issues with units, I guess sometimes might pop up.
Yes, yeah. So fortunately, these papers have some stuff on SI units and things, which is a good place to work on that.
Okay, so I'll let you go then. I'll see you at the end.
Good.
All right. Bye.
Okay. Bye. Right. Okay. Looks like I am by myself here. So, welcome, my mysterious audience. So we're going to be going through this paper. So question 1 is about elastic extension, and in general, this is a sort of Hooke's law and basic mechanics question. So part A is it's one of these you know it or you don't type questions. Extend it elastically, and so the definition of elastically is that something goes back to the way it was before. So in the case of a wire that's been extended, that means that it's going to have to go back to being the same length after you take the force away. So yeah, that's that one. There's not really a great deal to it. The SI one is a little more involved. As I think I've mentioned before, but as I will go over again, I think the most useful way for doing SI units, at least for a lot of people, is actually to figure them out from equations that you know. These can be a variety of ones. You can pick any you like. In this case, I'm going to borrow the kinetic energy equation. And specifically, we're going to say that energy is proportional to mv, oh, that didn't draw, v squared. And from this, we can say that energy has units of kilograms meters squared per second squared, where we've just squared the units of velocity. And then per unit volume is going to give us, if we bring this over here, meters to the -3. And if we multiply the two together, we are going to get exactly what we were looking for up here. So rather than trying to remember the various SI units of all of the different quantities that you can do, I think usually the most useful way of doing it is to work them out from simple equations and go one step at a time. It saves you a lot of memorization, rote memorization that way. Okay, let's have a look at this next question. So, for a wire extended elastically, the elastic energy per unit volume is given by this thing. So this is a, what do you call it? Dimensional analysis question, which means we're working purely in terms of the dimensions here. So again, this one, we need the units of each thing. We've just worked out the units of energy per unit volume, x, and so we know that those are going to be the same as the units of the right-hand side. So in this case, we would be working again from the units of epsilon, which is strain. Strain is force per unit area. And E, which is the Young's modulus. E is a little more tricky of a one to do, but it actually has units of newtons per meter. I'm not going to go through the extended maths of it or the extended kind of formalization, but you can get the SI units of strain and of the Young's modulus, and from that you can find that C will have no units. So what you should be looking to find here is essentially that the units of X match up with just the units of epsilon squared E, and therefore C has no units. All right, let's move on from that then and look at question 2. So, distinguish between mass and weight. So this is the one where we're talking about mass being the physical mass of an object, and that doesn't change unless you physically lose mass. You know, your mass is constant unless you chop off your arm or something, which is highly inadvisable, I may add. However, weight is dependent on the force of gravity. So weight is the force due to gravity on an object and will be proportional to the gravitational acceleration times the mass of that object. So your weight could vary on, Earth, the moon, Jupiter. Your mass would be the same, but you would feel heavier. It's actually your weight that you measure when you measure things on scales, even though they give you your mass, which is deeply unhelpful when people then try and learn the difference. But Yes. All right, so that's that. That's, again, unfortunately, that's just a sort of learned one. There's not a lot of deep insight to that, I'm afraid. Continuing on, part B. An object O of mass 4.9 kilograms is suspended by a rope A that is fixed at point P. They like to use a lot of letters in these, so it's a useful technique to be able to work out what's going on from all of these letters and your diagram. Generally speaking, and what's often useful to do is actually label any extra information from the text on the diagram. I think that's a useful thing to do here. So in this case, the only extra piece of information is the mass of object O, which is here 4.9 point. I can't do a point. This software is not terribly good. 4.9 kilograms. There we go. That's almost a point. It'll have to do. So in this case, there wasn't too much, but it's useful nonetheless. And below here, we're given that we have a tension in this rope of 69 newtons, and rope B has a tension of T. Okay, so on figure 2.1, draw arrows to represent the directions of all the forces. So conveniently, we basically just did that. The only one remaining is the force of gravity, which is going to act downwards, we would hope. Otherwise, bad things will start to happen. And that's going to be proportional to g times its mass, but it's important to note that they didn't actually ask for numbers here, they just asked for directions. It's always worth answering just the question you're given. Not any more, and definitely not any less. Okay, so calculate the angle theta. So I believe we have been told that this is in equilibrium. Yes, so it's held in equilibrium, and that means it's not going anywhere. So that means that our net force has to be 0. So we're going to need to resolve in one of two directions here in order to determine theta. And that's going to need to be vertically, since we don't actually know t in the horizontal direction. So we're going to resolve 69 sine theta by doing our trigonometry. Here's our right angle triangle. We're looking for 69 sine theta going directly upwards and 4.9g going downwards. And they're going to need to be equal to each other. And from that, we're going to be able to work out theta. And in this case, which we can just find from the mark scheme quickly, theta is going to be 44.1 degrees, apparently. Isn't that nice to know? So 44.1. Again, I can't do points. It doesn't read for a while. It's slightly frustrating. So, and then we're going to find the tension T. And similarly, when we're looking for the tension T, we're going to this time need to resolve horizontally. So in this case, we're now looking for 69 cos theta, which we now know because we know theta is going to be equal to T in the opposite direction again to balance out. And so 69 cos theta is going to be 49.6 newtons apparently. And yeah, that's going to do it for that question. This is all about resolving and balancing forces. The key here is recognizing that A, in equilibrium means that our forces in opposite directions need to be balanced. B, being able to resolve our at an angle 69 Newton force with sine and cos of theta along the right angled triangle. And okay, let's leave it at that as our two core points. So resolving the force and understanding that equilibrium means we're needing to balance it out. Those are a good 2 points to focus on from that. All right, moving on then. So, question 3. We're going through this remarkably quickly at the beginning, at least, but I think so far the questions have been reasonably simple. They haven't been anything too out of the ordinary so far. I'm guessing that, sadly, this will not stay the case. Part 3. An object falls vertically from rest through the air. So, this is going to start sounding very much like a SUVAT question. State and explain the energy conversions that occur as the object falls. Perhaps slightly less SUVAT then. So, energy conversions. We've got 3 going on here. As we would guess, a little bit of exam technique from the 3-mark question. That's always a useful thing to be doing in any exam, is working out what you're doing from the number of marks. We have 3 marks, we're going to have 3 energy conversions probably. So, the first one, we are converting from potential to kinetic energy as we fall vertically. As we fall, we are losing potential energy, and that is turning into kinetic energy of our object. Secondly, we are falling through air. That means that we are going to be dissipating energy against the resistive force. We are doing work against air resistance, and that is converting energy from our kinetic energy into heat energy of the air. So when you dissipate energy against a resistive force, be it friction, air resistance, drag in water, whatever it is, what you are actually converting it to is heat energy of the medium or of whatever is providing the resistance. So heat energy of the air, of the carpet, of the fluid, whatever it may be. So we're losing energy from potential and it's being converted into kinetic. We are dissipating energy against the air resistance, and that is being converted into heat energy of the air. Yes, so that's what they were. That was what they were looking for, essentially. Yeah, there's not a great deal more to it. They were. That's interesting. Yeah, so in the mark scheme they've slightly separated things out, which is a curious point to note, but it's worth saying, I suppose. In the mark scheme, they've described that we are gaining kinetic energy because we are gaining speed. Realistically, I would be inclined to argue that, in fact, that we are gaining speed because we are gaining kinetic energy. But I suppose I shouldn't argue with the examiners too much. Anyhow, moving on rather rapidly from that, we're going to continue on to a ball of mass 150 grams being thrown vertically upwards. It's always worth putting an extra word in the middle, because otherwise you start throwing things up, and that's never healthy. So we're going to throw vertically upwards a ball of mass 150 grams with an initial speed of 25 meters per second squared. Initial kinetic energy, well, that's really rather simple. 3 marks, I think, is quite a lot. So that's a nice question. We have our kinetic energy equation, half mv squared. We will put that in here as the key point to the question. And yeah, we put numbers in. We know m, we know v. The only thing to be careful of here is that we're in grams, not kilograms. And so, in fact, our mass is 0.15. Once again, I can't draw a point here. Kilograms. Because when we're dealing with actual physics and energy, we want to be working in kilograms. That's the only thing of note here. Okay, second part. Our ball is going to reach a height of 21 meters above the point of release. For the ball rising to this height, calculate the loss of energy of the ball due to air resistance. So this one has a little more to it. So what we know is if we rise to a height of 21 meters and this is our maximum height, then, which it hasn't really definitely stated, but yeah, I'm assuming that Yeah, so it is. Okay, so really that should say a maximum height. That's a slightly poorly worded question, but again, that's all they ever ask, so it's all we ever assume it to be. So for a ball reaching a maximum height, at that point we have converted all of our kinetic energy away into potential energy. At its maximum point in any trajectory, I'm drawing it sideways, in this case it's actually going straight up and straight down. At its maximum point, we are stationary. We are not going up or down at the top, and therefore it has no kinetic energy. So at this point, we want to say, well, okay, we've got mgh is our potential energy. And what we're going to find here is that, in fact, our mgh is not entirely the 16 joules that we would have calculated up here for our kinetic energy. It comes out apparently to be 15.9. Is that it? Oh, I'm not completely sure. No, apparently we calculated 47 joules up there, and we calculated 47 joules up here, and we would have found that the mgh gave us about 31 joules down here, and so we would be losing approximately 16 joules. So yeah, in this case, you're looking to say, okay, how much energy does the ball have at the highest point? How much did it have at the start? These are in two different forms, but these are still the energy of the ball. That's what's important here. And so what's been lost is the difference. The key point here is about realizing all of your conversions of energy, which is what we are bringing in from 3-part A. That's why they've included these in the same question. It's always worth bearing in mind things from earlier parts of a question, because there is usually a reason that they've put that there. The bookwork usually does tie into the rest of the question quite well. Last part, the average force due to air resistance. So the key here is average force. Average force means we are assuming that we have one constant value of the force over the whole course of flight. This isn't actually true, but that's why we're calling it the average force and not the actual force. And what average force most importantly means is that we can use work equals force times distance. In this case, our work done against air resistance is the energy that we've lost, 16 joules. We know the distance, it was 21 meters from up here, and therefore we can find out the force. That's that question. Again, slightly more involved, but not too bad as long as you go step by step. Okay, part 4, now we're getting quite different. We're on to pressure, we're on to gases now. Gases are a little bit more complicated, generally speaking, at least as far as the equations go. So first of all, define pressure. Once again, this is purely something that you need to know. Define pressure, force divided by area. So at this level, at least, these ones tend to be nice, simple equations. When they say define a certain quantity, generally they're actually just looking for the equation for that quantity. And in this case, that's force divided by area. Force per meter squared, essentially. B, use the kinetic model to explain the pressure exerted by the gas. So the kinetic model of a gas is the one which says we've got lots and lots of small non-interacting particles. Non-interacting means that the only time when one gas particle affects another gas particle is when they physically hit each other. And apart from that, they are purely free-flying. It also assumes that they are small enough that they don't actually take up any significant volume of the space that they are flying around in. The kinetic model, wow, that was poor speech there. The kinetic model explains pressure by saying when we have a container and we have gas particles flying around in it, when they bounce off a container, the container is exerting a force on the particle. And Newton's third law says that if that's happening, the particle is exerting an equal and opposite force on the container wall. The net sum of all of these collisions from all of these particles is what produces a pressure. And because the larger the area is, the larger the force will be. That's why pressure is measured in force per unit area, because it's simply proportional to the area. So in the Mark scheme, the points that they have are, we have constant random motion. That's our kinetic model. The molecules change momentum when they collide with the walls, which is what we were talking about earlier. Therefore, they are exerting a force on the walls. So that's the little extra step that they're looking for here, is this idea that when you change momentum, you are exerting a force. Force is the change in momentum over time, and in this case, that's an instant change in momentum, which is called an impulse. So when they collide with the walls, there is a force exerted on the molecules, and therefore a force exerted on the walls. And then lastly, they're looking for us to say that the force per unit area is therefore the average of lots and lots of collisions over a certain area of the wall. There we go. Pressure explained in a nutshell. It's a lot of things bouncing off a wall. Nice and simple when you think about it that way. One hopes, at least. Lastly, explain whether the collisions between the molecules of an ideal gas are elastic or inelastic. Now, it's important to note, as compared to the stretching of a metal wire earlier, in this case, what we mean by elastic is whether we conserve the kinetic energy, the total energy. And actually, that's the first point that they want us to make. So a lot of the time, even at A level, it's important to state the obvious, even when it doesn't seem to be being asked by the question. So here, they've asked us to explain whether the collisions are elastic, but half of the marks are just for telling them what elastic means. So it's always worth doing that. In the same way, above, they've asked us to use the kinetic model, but most of the marks in that question were for describing the kinetic model. So that's important. In a lot of questions, it is very worth taking the first sentence or two of your answer just to explain the base concept before you actually get on to explaining whatever it is they've asked you. It's a little dull, it's a little frustrating, but it's a very important part of exam technique because it is consistently worth a large number of the marks. I used to find it very frustrating myself, but it's important nonetheless. So in this case, we say, okay, for a gas, elastic, or for collisions, elastic means we conserve kinetic energy. For a gas, the temperature is constant in an ideal gas. The temperature is constant, and the temperature is a measure of our average kinetic energy, which means, yes, we are conserving the total kinetic energy, and so, yes, the collisions are elastic. All right, so that's that. This one hasn't involved any maths, actually. It's been purely answer-based. Some people will like that, some people won't, but there's all sorts in these papers, and that's important to practice on too. Moving on then, question 5. We're probably going through this paper fast, so we will see afterwards whether we want to go back to some of these questions in more detail. But we seem to be doing fairly well, so we'll see how it goes. We will see how this goes. Question 5 then. State 3 conditions required. These. Oh yes, I'm being dumb here. So question 5. This one's got a little more going on. This is interference. This is a bit more complicated. So, state 3 conditions required for maxima to be formed in an interference pattern produced by 2 sources of microwaves. So, first thing to note, microwaves. Microwaves, just like light, are electromagnetic radiation. They are light, but at a lower frequency. They are longer wavelength than regular light. So our conditions for maxima to be formed when we have two sources of microwaves. The first is that our sources overlap at all, right? If our sources are on different sides of the planet, then no, we're not going to form maxima. Again, it's kind of stating the obvious. The second one, coherence, constant phase difference. So what that means is that when our sources relative to each other aren't just kind of wandering about in terms of their phase. They have to be coherent. And just writing down the word coherent is enough here. So I would advise that sticking with just knowing that a condition for maxima to be formed is coherence. Coherence itself is quite a complex topic in terms of studying constant phase difference of sources. So I would stick with that. Forming maxima requires that the path difference be some whole number of wavelengths at the maxima themselves. So now we're talking about the actual maxima rather than the sources. So to form a maximum, at that maximum, we need a whole number difference of wavelengths so that our wavelengths line up one on top of the other so that their maxima align. This is constructive interference. This is going to form a maximum. That's what we need to form our maximum. The last one, which is a kind of bonus point, so you needed 3 out of these 4, is that they have to have the same polarization or to be unpolarized. That one is a little more out there as far as A-level goes. You don't really deal with polarization, but they're accepting it. I would assume because someone's written it down in a previous year, and it is true, even if it's not specifically taught in this course. So there we go. We need them overlapping. We need coherent. So let's write these down. We need overlap. We need coherence. That doesn't even moderately look like the word coherence, does it? There we go. We need overlap. We need coherence. We need a whole wavelength path difference. That's our condition for an actual maximum. And then I would argue that those are the 3 most important ones. The last possible one was to say same. Okay, that's not even words at that point, is it? One day, the software that I mainly use will work again, I promise. Anyhow, we will continue, once again, my mystery audience, to part B. A microwave source M emits microwaves of frequency 12 gigahertz. So, show that the wavelength of the microwaves is 0.2025 meters. This one is actually nice and simple, realistically, as long as you're using the right equation. So in this case, we need to remember that microwaves are essentially light. They are electromagnetic radiation. And for that, we have the equation C equals f lambda. C, of course, being the speed of light, 3 times 10 to the 8 meters per second. We know the frequency, so lambda is going to be c over f. And if we do that, I assure you, we will come out with 12 gigahertz. That's actually a very nice question. That one's nice and easy. We will move on. That's just putting numbers into an equation. Part C. So now we've got a complicated looking diagram. We have 2 slits and they are placed in front of a microwave source. Now, I'm going to stop here to relate this back to question A, just briefly. This is why so often we deal in double slit experiments with one source behind them. By doing this, we ensure all of the conditions in part A, aside from the one which defines, where the maxima are. That one's only ever satisfied at the maxima, obviously, because that's the condition for a maximum. But this ensures that we have coherence because they are from the same source. And a source is coherent with itself because it's the same source. So this assures coherence. It assures the same polarization because a source only has one polarization. And it assures that they will overlap because they're close together. So yeah, this is why you always see these double slit experiments, because they assure that you will meet the conditions so that if you have the right screen, the right angles, you will get the maxima that you are expecting, and not, that you won't have some fault with your sources that means they don't line up and nothing works. That's why these are so common. And it's good to see these questions relating into each other sometimes, I think, to see a little bit of the bigger picture. The distances S1 to O and S2 to O are equal. So what that means is that they are evenly spaced about this midpoint that relates to O. A microwave detector is moved from O to P, P being over here. The distance S1P is 0.75 and S2P is 0.9. They're very fond of describing the diagram. So far, they haven't told us anything new. The microwave detector gives a maximum reading at O. This is unsurprising because we have equal distances, and so they're going to be in phase at that point. There is no path difference, which is 0, a whole number of wavelengths. Therefore, we're going to get constructive interference, and we're going to get a maximum. State the variation in the readings on the microwave detector as it is moved slowly along the line from O to P. So, this is a curious one. This is, I would argue, a hard question, actually. However, what we do need to remember, and it would be easier if we had a sheet of paper in front of us, to be sure, but we know from up here our wavelength. Our wavelength is 0.025 meters, which is, of course, 20. I say, of course. It is 25 centimeters. Yes. No, it's not. It's 2.5 centimeters. Cool. I'm doing well here. So, it's a number of centimeters. It's 0.025 meters, more to the point. Anyway, continuing on. Here, we know our path difference. Our path difference here is, in fact, 0.15 meters. And that is a whole multiple. Specifically, it is 6 multiples of our wavelength. So our path difference here, delta lambda, equals 6 lambda. What does that tell us about our maximum? This tells us that we are going to have a maximum at P. More importantly, it means it is going to be the 6th maximum out from our microwave detector. So as we move from O to P, we are going to meet 6 maxima, aside from the middle one at O, with the sixth one being at P itself. So it's going to go from being at a maximum at O, down to a minimum, back up to a maximum, and repeating until we hit a 6th maximum at P. Yep, okay, cool. That was what they were looking for. Always promising. So we're going to say we have maxima and I should really learn to do joined up handwriting. I look like a child now. Maximum and minima, and P is the 6th maximum. That looks awful. Never mind. Continuing on, you didn't come here for my artistic talent. I mean, I don't know. I'm talking to no one at the moment, so perhaps you didn't come here at all, and no one will ever see this, but that would be rather disappointing. For part D, the microwave source M is replaced by a source of coherent light. State 2 changes that must be made to the slits in figure 5.1 in order to observe an interference pattern. So, number 1, we're going to make the slits narrower. Number 2, they're going to be closer together. Why is this? It's because the size of our experiment needs to be similar to the wavelength of the light that we are dealing with. Microwaves have longer wavelength than actual light. So as we make the wavelength shorter, the slits need to get narrower and the gap needs to get smaller to match the reduction in wavelength. It's interesting to note that they've said we're replacing it with a source of coherent light. The microwave source itself had to be coherent in order to make all of this work in the first place. So that part is slightly odd, but what they really mean is a source of laser light. As I've mentioned to some students before, at least, and I will mention again here, when we talk about we have a source of light for all of these sorts of diffraction experiments, and it's of a certain wavelength, we are talking about a laser. And that's because, like the double slits, that satisfies the conditions of coherence, of constant phase, and of a single wavelength. All right, so moving on. Question 6, just 2 to go now. We have 2 resistors, A and B, with resistances R1 and R2 respectively. We have a battery with an electromotive force and 0 internal resistance. State the energy transformation that occurs in the battery. So this one is asking you essentially to just know, how do we store energy in a battery? And the answer is chemically. So we're transforming here from chemical potential energy to electrical energy. Then in the resistors. Resistors dissipate energy as heat. That is the definition of a resistor, in fact. So in the resistor, we are converting electric energy into heat energy of the resistor. If we get hot enough, we will also make some light energy because they'll start to glow, but at that point, things start to burn and melt, and that's generally a bad idea. So for a pure resistor, we're just talking about heat. They could, however, be a light bulb or something, in which case you would get light as well. But yeah, so generally speaking, the battery, chemical to electrical, chemical potential to electrical, the resistors, electrical to heat energy. The current in the circuit is I. State the rate of energy transformation in the battery. So in a battery, we have P equals IV, or P equals EI in this case, because we have because our voltage is our electromotive force because we have no internal resistance. So the energy transformation in the battery is P equals IV, the power of the whole circuit. P equals IE, since E is V. So here we have P equals IE. That's not an E, that's a V. We can turn it into an E and pretend we never made that mistake. Aren't we clever? No, we're not. You're looking like an idiot, Conrad. Never mind. Continuing, the resistor A. So A has a resistance R1. We have a current I. That's nice and simple. P equals I squared R. P equals I squared R1. There we go. The other point to make is that up here for the battery, we could have said, well, also the battery is powering the circuit as a whole. And so it could have also been, and these are the same thing, bear in mind, I squared brackets R1 plus R2. And this is because the resistors are in series, so the total resistance of the circuit is R1 plus R2, and therefore that I squared total resistance is the total power of the circuit. Part C, now, this one's a little more interesting. Our resistors are made from metal wires. Data for the resistors are given in figure 6.2. So often, in fact, a resistor is in fact a long, usually coiled up to make up for the really, really long length, a very long piece of wire. We tend to imagine wires as these ideal things with no resistance. In fact, everything has resistance, and a really long wire has a significant enough resistance to be used as a resistor. In this exam board, it's not true, but occasionally you will see a resistor which is a wire drawn like this instead of as the usual box. That's actually the American system for drawing resistors, if you are interested. It's worth knowing about just in case you come across it and you're not sure what you're seeing. In America, that is just generally a resistor. It is often otherwise used to mean a resistor which is specifically a long coil of wire. Not to be confused with a curly loop version, which is an inductor. That's why we tend to use a box, because they're less similar. Anyhow, resistor A has resistivity ρ, length L, and diameter D. B has half the resistivity, twice the diameter. So, we have already, and we are looking for the ratio of the power dissipated. So, we have already said that P equals I squared R. So in fact, when we look for PA over PB, we are going to end up cancelling out the I squares, looking for, in fact, RA over RB. Okay, that's a little simpler. And now we're looking for the equation, which is R equals rho L over A. All right, so it's worth noting here that resistivity has slightly curious units of resistance times length, but there we go. It is proportional to the resistivity, it is proportional to the length, and divided by the area. What that means in sort of real English terms is that the resistivity is a property of the physical, of the metal itself, of the material. That's it. And it's how resistive a metal is. But also it's saying that if a wire is longer, it has more resistance because the electrons have further to travel. But if it's wider, if it's got a bigger area, it has less resistance because there is more space for the electrons to move through. That's a good way of thinking about it. In this case, we're going to discover that actually, I think the power dissipated is the same. No, it's not. It's 8 to 1. We're squaring things because pi d squared over 2 or whatever. But yes. So anyway, you can put those in. Area is pi r squared, or pi d squared over 4. Yeah, that's a bit weird, but there we go. You can put the numbers in. You can come out with a ratio just by substituting rho LA for your resistances going from here to here. All right, last part of this. The resistors A and B are connected in parallel across the same battery of EMF E. Determine the ratio power dissipated in A over power dissipated in B. This one is slightly more curious, but at the same time rather simpler. So some people will get very stuck on this question. However, it's important to see the trick here, and this is one where a little bit of insight goes a very long way. So first, it's worth noting, this is a 2-mark question. 2 marks is not a lot, so they're not really looking for much here. What we are looking for is saying, actually, in parallel, voltage is the same. And by rearranging our equation and combining the two, we can also know that P equals V squared over R. And so at that point, we can say that PA over PB equals RB over RA. And we can put the same calculations that we did up here into effect once again for RB and RA, but just flip the ratio over. Okay, the final question I went over last time with the students at the moment, but for posterity we will talk through it a little bit in brief. This is the alpha particle scattering experiment. So the 2 main results of the alpha particle experiment are the core here. And they are things that you do really need to know. The first is that most alpha particles, by a large, almost all of them, go straight through a sheet of metal that they are fired at. That is really important. Almost all of these alpha particles go straight through as if there were nothing there. However, the remaining fraction, rather than being deflected by a little bit, some of the ones are deflected by a little, but most of them just fly straight through. However, there is a small number which are essentially bounced back. Not necessarily bounced directly back, but they're going in like this and they're coming out like this. Whereas most of them, let's make that look like a T, are just going straight through or at a very slight deviation. Some are getting bounced back. Those are our big results for the alpha particle experiment. Relating them to conclusions, result 1 is saying, okay, if I'm firing particles and they're just going straight through, and almost all of them are going straight through, well, the only thing they're going to go straight through is empty space. And so if almost all of them are going straight through, then almost all of these atoms, because this is a solid wall of metal atoms that we're firing them through, almost all of those atoms must actually be empty space. When this was done, this was a huge, huge deviation from the previous plum pudding model that they had. So result 1 is that almost all of atoms are empty space. We're fairly comfortable with that these days. Result 2 is we have alpha particles bouncing off. The fact that they are bouncing off tells us 2 things. It tells us that we have a very small, very dense, positively charged nucleus. We know it has to be positively charged because it is reflecting alpha particles, and alpha particles are positively charged. if they're reflecting off each other, if they're forcing each other away, they must be repelling, so they have to have the same charge. So we know that the nucleus is positively charged. The second part, we know that it is small and heavy and dense. And this is because it's bouncing the alpha particles back. If it was light, or if it was, big and soft and fluffy, then it wouldn't be bouncing them back. It would be getting knocked around by the alpha particles. So we know that we have a small, dense, and positively charged nucleus, and that most of the atom is empty space. Those are our two results. So it's most, I don't know why I keep drawing two lines, most empty, small nucleus with, how should we say this? We'll say almost all of the mass of the atom is in that nucleus. And it's positively charged. By the way, just to say, as a last point for exam technique and just sort of saving yourself time in general, plus VE and minus VE for positive and negative are very useful and completely widely accepted shorthands for positive and negative. It's just these little things, but saving yourself time is always worth doing because you are always time pressured in an exam. Okay, that brings us to the end of this paper. We've spent almost an hour on it. I think that's a reasonable amount of time. So yeah, I will call an end to this there. We will return to the beginning of the paper, and I will leave you. I hope this has been helpful to you all, and I will see you next time on Conrad's question paper live streams. I should develop a name for this series. I think that would be good. Cool. Yeah. All right. Bye-bye then. Hi, that's me. Didn't really intend to do that, but that will do. Goodbye.